Hi guys, welcome back to our YouTube channel Think in Code. Today our topic is dynamic casting, RTTI and type ID in C++. So today what we are going to see in this video, why we need dynamic cast, what is dynamic cast, relationship between dynamic cast and RTTI, successful dynamic cast example, dynamic cast failure example, detailed explanation of RTTI, uses of type ID in C++. Why we need dynamic cast? Before going to dynamic cast, let me explain what are the different types of casting available in C++. One is downcasting, second one is upcasting. So these two things comes to the picture when we are dealing with pointers. Without pointer, this type of casting not possible. Coming to the first one, upcasting, is always safe type cast because here a base class pointer can always point to the derived class object or base class object. These two things are always safe. You might think how base class pointer can point to the derived object safely because those two are different type. So here inheritance comes to the picture. A derived object always have base part plus derived part object combined. So logic is base class pointer actually pointing to the base part of the derived object, but it has two conditions. If base class pointer cannot point into the derived object, if inheritance mode between base class and derived class is private or protected. Because in these two inheritance modes, visibility of base part of derived class is hidden by outside of the derived class. But we can create a base class pointer and point into the derived object inside the derived member function. However, inside derived class, it knows it has base part, but outside of the derived class, it hides the base part. When it comes to the second one, downcasting, which is a dangerous one, because here we have two situations. One is if a base class pointer pointing to the derived object, then we can safely downcast, like base to the derived, because base contains derived object. Second one, if base class pointer pointed to the base class object, then if we try to downcast like base to derived, but base actually have base object, not derived object, which is dangerous. So this is all about downcasting and upcasting. I hope you understand everything about casting. So now let's understand why we need dynamic cast. Dynamic cast is needed for safe downcasting. So what do you mean by safe downcasting? So if baseless pointer is pointing to derived object, then we can do safe downcast. If base is pointed to the base object, we cannot do safe downcast. As a user, we don't know base class pointer is pointed to base object or derived object, which is known only at runtime. That's why we are using dynamic cast. So static cast does no runtime check. So wrong downcast compiles but cause undefined behavior. Now let's understand what is dynamic cast. Dynamic cast is a C++ cast operator used to convert pointers or references within an inheritance hierarchy safely. It performs a runtime type check and succeeds only if the object type is compatible. So let's understand this statement, what it tells. As you know, we have two situations. One is base pointer is pointing to derived object where we can perform safe downcast. And second one is the base class pointer is pointing to the base object. We cannot perform downcast. This dynamic cast operator actually check the actual type of pointer at runtime. If it is pointing to the derived, it will perform downcasting safely. Otherwise, it will return null pointer, which means downcast fails. So now understand what is the relationship between dynamic cache and RTTI. Dynamic cache depends on RTTI to identify the actual type of an object at runtime. RTTI information is generated only for polymorphic class, which means a class at least contains one virtual function. Dynamic cache uses RTTI data via vtable to verify type compatibility before casting. Now let's understand this statement. So if we have at least one virtual function, it creates the B table, which has virtual functions along with RTTA pointer. This RTTA pointer pointed to the RTTA table, which has actual object type info. Here we can see relation that our dynamic cache needed actual type of our object, which is available in RTTA table. So to have RTTA table, we must have V table so that we can access RTTA table via RTTA pointer, which is in virtual table. but vtable created only if a class contains at least one virtual function. So the conclusion is without RTTI, dynamic cache cannot work properly. So let's understand how to use the dynamic cache with examples. So let me show some examples why we need dynamic cache instead of static cache. So let me show an example related to static cache. So in this example, I'm creating one base class. It consists of one virtual destructor and I'm creating one derived class. The mode of inheritance is public and it has one member function called show. In main, I'm creating one base class pointer. It holds the base class object. Here I'm trying to convert base class object into derived object, but here base class pointer is pointing to base object. Still we are trying to access the derived class object, derived class member function. Does it make any sense? No. That's why we are going for a dynamic cache. So let me show an example related to dynamic cache. So in this example, I'm creating one base class and it consisting of one pure virtual destructor which enables the RTTI. Here I'm creating one derived class. The mode of inheritance is public. It has one member function called show. In main, I'm creating one base class pointer and it holds the derived object. Then I am trying to convert base class pointer into derived object. If the dynamic cache is success, it will return the derived pointer. Otherwise, it will return the null pointer. We are checking that condition here if the dynamic cache is success or not. So let me compile and run. So we can see here output displayed as dynamic cache successful. Whereas in another case, we try to access where base class pointer is still pointing to base object. Then we are trying to convert base class pointer into derived pointer through dynamic cache. If it fails because base is pointing only base object. So let me run and check. So there is no output is printed because here base class pointer pointing only base object. That's why dynamic cache failed here. So we can't able to access the derived member function via base pointer. So let's discuss what are the cases where dynamic cache fails. A dynamic cache fails occurs when the base class pointer reference do not point to the target derived object. For pointers, dynamic cache returns null PTR. For reference, it throws a bad cache exception. So let's demonstrate with examples. So in this example, I'm creating one base class with a virtual destructor and I'm creating one derived class. Here I'm creating one base class pointer. It holds the base class object. And we are trying to convert base class object into derived class pointer. Here dynamic cache fails because base class pointer pointing the base object instead of derived object. So that's why here derived pointer holds the null PTR. So if the if condition is true, it will execute the dynamic cache fail. So let me compare and check the output. So we can see here dynamic cache failed. So let me show another example where dynamic cache failed. So in this example, so we can see in main, I'm creating one base class object and I'm trying to convert base class object into derived reference. Here also dynamic cache fails because here base is pointing only, we are creating base class object and we are trying to convert derived class reference. So that's why dynamic cache fails. So it will throw an exception called bad cached exception. Here casting becomes failure. So let me check. So we can see here dynamic cache failed, bad cache caught. So let us understand the detailed explanation of RTTA. It means runtime type information. So RTTA allows C++ to determine the actual object type at runtime, not just the pointer or reference type. So at compile time, we only know the what is the type of the pointer, but not how what is the pointer is holding. So RTI is available only for polymorphic class, which means the class consists at least one virtual functions, as we discussed previously. Each polymorphic object contains a vptr that points to the vtable. The vtable internally holds a reference to RTTA data, and dynamic cache uses RTTA to check whether a cache is valid at runtime. Type ID uses RTTA to return type information via a type info object. Internally, type ID uses the RTTA table, RTTA consisting of all type object info, that is class and actual type of data. So RTA helps prevent unsafe downcasting and undefined behavior. So when we create a derived object consisting of virtual pointers and its data members. So here virtual pointer is pointed to virtual table. So virtual table has virtual functions and RTA pointer. So RTA pointer points to the RTTA table. It consisting of type info object like class name, what are the actual data type. It contains all the information about the object. So let me explain the uses of type ID in C++. Type ID is used to get type information of a variable or object at runtime. It returns a type info object. So here let's see the syntax type ID expression or type ID type used mainly for type comparison and debugging. So let's demonstrate with some examples. So in this example, I'm creating a variable called x and storing 10 into it. So your type ID returns the reference to the type info object. To know the actual name of that object, we use that member function called name. So t.name. It will print actual name of the data type. Here see I means integer. So let me explain another example. So in this example, I'm creating one base class and one derived class. I'm creating one integer variable and double variable. So here type ID of A returns the reference to the type info object, and we are calling through one member function called name. So it will print here int, and the second print statement cout returns the double D. So we can use type ID to compare the two objects whether they are same or not. So this is the syntax we use. This type ID of A means integer, which is equal to actual type int. So condition true. So that's why it's print A is int. So type ID with polymorphic. So here we are creating a base class pointer. It holds the derived object. So here star BP means what is the actual data stored by the base class pointer. It will display. So let me run and check. So here I means int, B means double, and we are comparing A with actual type int. So the condition is true. That's why it is print A is int. Here 7 derived. What is meant by 7 here? So here baseless pointer pointing to derived object. That's why print derived class length. That's why it will print 7. Here baseless pointer pointing to derived object. That's why it will printing derived. So let me check another example. So in this example, I am creating one class without virtual function. So I'm creating one derived class. So in this I'm creating one base class pointer and holding the derived object. So if you write star a, here star a holds the derived object. So that's why it will print dog actually. but we the output is displayed as 6 animal because here the class base class doesn't have any virtual function. So there will be no concept of virtual table and arbitrary function. So that's why type ID is not work properly here. So if you want to know what is the type of the A, so we can just type the A and we can know the what is the data type of the A. Here we can see P6 animal. P means it is a pointer type and 6 means so the length of the class name, base class name, that's why it is 6. That's why it is printing P6 animal. Thank you for watching this video. Please subscribe and share with your friends.